So we can have a look at the noise as well, having dealt with a bit of the transient response and a bit of the compensation and the overall design strategy, that sort of thing. One thing we haven't actually looked at is the small signal response. So this is V out over V in. Well, it's actually just V out, but V in is 1. So it is V out over V in, even though I didn't actually divide through. We can see we've got a full gain from, by the looks at about 2 Hertz. There's a corner here somewhere, up to probably about 200 kilohertz before it starts to fall away. We only really need 20 Hertz to about 20 kilohertz, so it should be flat in that region with relatively little phase shift. We don't want too much phase shift in that region, because if we have multiple speaker cabinets, each being driven from a different amplifier in some large speaker system or sound reinforcement system, you don't want to have accidental phasing between the various channels, because you'll get highs and lows in the room that's periods of superposition where the output of 2 speakers are in phase, and periods of nulling where the output from 2 speakers is in antiphase. And of course it doesn't sound very good in the crowd. You've got these bits where the sound is awful, and you've got these bits where the sound is really good or a bit peaky in certain frequency ranges, and the crowd are upset. So generally speaking, you don't want your amplifiers to add any phase shift in the region of operation. You leave that to your sort of acoustic controller or set of DSPs, whatever's actually setting your room up, if you're interested in that sort of thing. If it's just the only amplifier in your system and you're going to have 2 of them and they're the same and everything, then it probably doesn't matter so much, but I would try to make it no phase shift in the region of interest anyway. So we haven't actually looked at this so far. I thought we should, because it's one of the first things that people look at usually when they finish it, but it's a given that you want it flat in this region, and that the gain should be the gain you designed for, which should be a 1 plus R10 over R9, and that should turn out to be whatever that is, 15 dB, which is about 6 over 1 is 6 in linear. What's 500 plus 500 over 500? 6. Magic. Good, isn't it? Right, so that's more or less all you can tell from that. There's not much else to say about it. The video is really about noise, so we'll edit simulation command, noise. We've got to tell it a V out, which is here as an output node. V3 is the source we want to compare with. This one is V3, it's an input source. 100 points per decade between 10 Hz and 20k. We don't need to see a very wide range in the noise. We're not looking for poles that are way out of band or anything like that. We are only interested in the noise that we're actually going to hear. And this is probably roughly the region of noise we're going to hear. If we want to integrate across this region, we don't want to integrate noise that's way out of band, because we're not going to be affected by it. So we'll click on the output and we'll see our output noise. 50 nanovolts per root hertz is what that says roughly, and that's in the mid band. People's hearing is most sensitive around this region. It's the region that people talking or singing, probably between about 150 hertz and about 300 hertz, I should think. This is the bit where your ear is the most sensitive. Down here, you feel it more in the frame of your body. Up here, it's all symbols and aliasing, because your MP3 wasn't encoded at the right bit rate, that sort of thing. So what we'd like to do is to be able to click on some component and find out how much it contributes to the noise of the amplifier overall. This is the output noise, and if we want a value in RMS, we'll press Control and click, and it will tell you 7.11 microvolts RMS. between 10 Hz and 20k. So it's just adding up the area under the graph. That's fine. And if we wanted to know our signal to noise ratio, you can say, well, my signal maximum is 1 volt or whatever it is, RMS, which is 1.41 if it's sine wave peak, and you can do, well, 1.1 volt RMS divided by 7 microvolts RMS that's about 100,000 difference, and 100,000 in dB is about 10 to the 5. 10 to the 5 in log, so convert that to dB, that's probably about 80 something. 80 dB of signal to noise, that's not bad. In fact, we can probably have a go with the world's worst calculator. 1/7, actually that's the other way around, isn't it? Alright, we'll do it that way. 7.15 was it? E minus 6. 139,000. How do I do 1 over that? There it is. Righto. Save that. Clear everything. 20. This is volts, so it's 20. Times. I bet I have to do that number and then press log, don't I? Yep. Go away. Memory recall. Log to base 10. Yeah, that looks about right. Times 20. 102 dB. Just to give you some idea, a CD player's noise floor, or the noise floor of the encoding of a CD, never mind the player, just the noise floor of the CD encoding mechanism for a good old-fashioned compact disc, is about 106 dB down. So we're not losing much. If you were to hook a CD player up to this and you had a well-mastered CD, you'd only be losing about 3 dBs worth of noise. So it might be worth fighting to get this a bit better, but actually we're not doing that badly. In practice, of course, there'll be a lot of things like power supply hum, the fact that somebody's left their mobile phone on top of the amplifier and they've got a text message. People's, I don't know, if you're in a big facility, there'll be porters and they'll have pagers, and if you live near a tram line, the tram will be arcing, you'll get a lot of EMC from that, and if there happens to be a thunderstorm, the lightning will produce EMC, and God knows what else, plenty of other things to worsen your... But these are all, this is all noise that's generated by people and their activities on the earth. What we're looking at here is the fundamental noise mechanisms caused by the movement of charged particles through our circuitry. And of course by the motion of atoms, just because they're not at absolute zero. So it's the shock noise and the thermal noise, and a little bit the flicker noise as well, but we're probably not in the flicker noise region. So this is the best you'll ever do from this amplifier, and if you actually built one on the desk, you would do worse. All resistors have a bit more noise than actually the prediction is because of the way they're manufactured. But 102 dB is perfectly acceptable. So let's just say we want to know, for the sake of our interest, how we can make it better. Well, if you've been in 225 and you've seen it through to the end, you'll know that I'm always banging on that the signal to noise is set early on in the system. So we ought to expect the first transistor and the components around here to be the ones that do all the damage. And by the time we get towards the end here, where we've had all the gain and everything, if these transistors add noise, well, there's no gain to amplify that noise before it goes into the output. So they have to add a lot of noise for it to cause a big problem. Whereas if this transistor and this resistor, or maybe this resistor as well, although it's a very small value so it won't have much noise, these produce noise, it gets amplified by this stage and this stage. This stage doesn't have any voltage amplification, but it has current amplification. So if it's a current that we're interested in, this also can provide amplification. So things down here at the front always get all the amplification, and by the time they get to the output, they're enormous, and they are probably the cause of most of the noise we can see. So we might have a little look and see what we can see. If I was to try this input resistor here, which is, the job of this resistor is to produce the same impedance looking out of the base as this, as is seen looking out of here. And because this is at DC, I should say, so resistance really. This pathway is blocked at DC by C6, this pathway is blocked at DC by C7, so as far as a DC is concerned, we've only got R10, then it goes through to here and we've got 8 ohms into the ground, which is not very much. And if you were to look through these transistors as a small signal when they're in there, they're just about conducting quiescent conditions, which is, I haven't solved the quiescent, I have solved the quiescent conditions, 57 milliamps. Looking up here into the rail, you will not see very much resistance at all, and the feedback will act to gravely reduce that resistance as well to something extremely small, which is what we really want. So we will see effectively 2.5k or whatever it is. I changed the value slightly from previous in order to help the transient response a bit. It was a fairly curious beast, but I think, and I'm not certain because I haven't spent very long looking at it, but I think I've pinned it down to the charging up of C1 and something to do with this network here, but I haven't quite pinned it down. I don't really need to though. We're never going to put fast edges into this amplifier, we're going to put music, and even if we have large sort of bass drum or whatever, the sort of frequencies involved don't extend to megahertz, and if they did we wouldn't hear them anyway, so it doesn't matter that we don't have a first order response on the rise, the transient response. If you really want the first order response, the only thing you can do to get that is to provide the phase margin which is consistent with the first order system, and the only way you can do that is to change your compensation. There was an element of that problem that was to do with this source, and there was an element of it that was to do with the charging up of the compensation cap and what happens to these transistors. And I suspect there is an element to do with the time constant that lives around here as well, which is very surprising to me. But I haven't quite pinned it down, I'm not sure. But I'm not going to go looking because I don't really need to, it's just a demo. Anyway, back to the noise. 50 nanovolts made up of some sources in here. If you have a look at that resistor, it adds 39, which is more than half of all the noise at the output is due to this resistor. So making this resistor smaller would be a jolly good idea if we could. It would also mean making that resistor smaller because we have to keep them the same size, and it would mean making this resistor smaller because if we changed this one and we didn't change that one, we'd be changing the gain. Changing the size of this resistor will probably mean changing the size of C5 because that and some other things as well form a time constant that determines how low in frequency the amplifier will actually amplify before we get to the low frequency cutoff. So you can't just go change it because you feel like it. You've got to consider other things as well. The other thing that's probably going to add a lot of noise, I suspect, is the first transistor. Sure enough, it's adding about 27. And if you sum 27 and 39, you'll get to somewhat more than 50. The reason for that is because they don't add up just by summing the sources. Uncorrelated sources sum with their squares, so you'd have to do the square of 27 nanovolts per root hertz and the square of 39 nanovolts per root hertz. Add those and then take the root, and then you will only get to this if they're totally uncorrelated, because that's our presumption. If they're correlated in some way, which I don't think they should be, but if they were, that would reduce the answer somewhat. So that's probably it. In the rough way of looking at it, it's that and that add up broadly to this. We've probably found it, but it's not exactly proof. So we could have a look at a few other things that are near the input and see if they contribute. Yeah, it's a bit. 4 nanovolts. That transistor? Not really. Not really. Not really. Not really. They're all living down here. Pretty much everything is going to be somewhere around here. Quite low values. We have found the dominant sources. Feedback resistor? Nope. That's too small to be bothered with, I should think. A reasonable amount. More than I expected. Nothing of note. Nothing of note. Anything past here probably doesn't add very much because most of the gain is happening here. The only things that really are over here will feel the gain of this, including apparently R19, which was a bit of a surprise to me. So if I was to get rid of some of this lot, I would just close it and rerun it. That one, and the output, and apparently that one as well, are the dominant sources. And we ought to try and make them smaller if we can. It would be probably quite nice to be able to get rid of that resistor. And if you look at some operation amplifier designs, the way that they get the very, very high input impedance that is desirable in an operation amplifier is they put some special circuitry in this space here between the input that you see on the outside of the chip, pin 3, non-inverting input, and this transistor, and between the inverting input and this transistor. They'll put some special bias circuit, and the job of the bias circuit is to provide just the right amount of current that this transistor needs to bias it into just the right region of conduction. A consequence of that is that if you have a magic box here that provides all the current that this transistor needs at DC, all you have to provide is the AC current to drive the transistor appropriately. And this can leave you with extremely high input impedance. The circuits are not terribly complicated, but from the point of view of noise, they have problems of their own in the sense that they will add shot noise, and they'll be injecting the shot noise in the spot where it will get the most gain. So it's not a panacea where you solve all your problems by replace the resistor with some circuitry. It would depend a bit on how your circuitry is designed and also the temperature you're working at, and so on and so forth. 52 nanovolts per hertz is fine at the output. We know that because we worked out the signal to noise ratio and we thought it was okay. I probably wouldn't bother to change this. I might get rid of R1 and R2 because I don't think they do much good. But this person who originally sent me the design had them in there, so I will leave them this time. One thing you might want to do is add some network here to filter out frequencies that aren't interesting to you. There's no point in amplifying hundreds of kilohertz if you're not going to hear it. All that will happen is you'll dissipate power in your load that you don't hear, and you'll dissipate power in your output transistors that you don't hear, and your transistor will get hot as a result. But if you're going to have some sort of if you're going to have some sort of preamplifier, you'll probably do your filtering then, so you don't have to worry too much. A couple of other things people might do. Sometimes they put a diode there in parallel with this capacitor and a diode, also sort of not back to back, but opposite and in parallel, all three in parallel together. The reason is if when they're wiring it up they make a mistake and this node gets raised or lowered quite a lot towards one of the rails, you won't accidentally charge this capacitor by more than 0.7 volts. You should never really get any DC on it anyway. And of course, if you accidentally charge it up the wrong way, it'll blow up, perhaps, which is, it'll make you jump, and if you're too close to it, you might get hit by flying debris. But I tend not to bother. I trust myself that I've blown enough of them up that I'll be careful. But of course, every now and then I still blow up anyway, even though I am careful. And you just have to take your risk. What else is there to do? Very little, really. I suppose we could have a look at the power output, which is not noise, but noise in this case hasn't proved too difficult. If you don't believe that this stuff doesn't contribute anything, I just click a few of them. You can't even see it. There it is, femtovolt. Nothing, effectively, compared to that. It's all on the axis. This one, yeah, same. Nothing. of thing. It's not no noise, but it's so small we don't have to bother with it too much. And the reason is that the noises that are being produced by this circuitry doesn't experience the large gain that we get especially in this stage. Right. We haven't spent a lot of time dealing with what causes the distortion either. We'd spent a bit of time making sure we dealt with the output stage properly, but we didn't really have to deal with these two. The fact is, in Class B, or AB, whatever you want to call it, amplifier, the output stage is the mean baddie, and the other two really aren't too bad. This one especially, it provides most of the gain for the global loop, so when there's plenty of gain in the global loop, that linearizes the amplifier in the sense that the current that you get here travelling into this base, or the voltage you get on this VBE, is whatever is needed to try and make the output look like a big version of the input. And other than the amplitude, there should be no difference in the shape. So that global feedback is lowering your distortion for you. It's also increasing your input impedance and decreasing your output impedance, which is good. And that's because of the way the feedback is applied. It's parallel derived and series applied. Sometimes they will call it shunt series as well, especially if you're looking in Gray, Hurst, Lewis and Meyer, Design of Analog Integrated Circuits, very good book on this topic. The book, I would say. There is another book by a chap called Ravasi. In fact, there's several books by that person which are very good about analog and RF design. But those two are excellent. Not affiliated with either, and of course I'm not either of them. So this stage doesn't really have a lot of distortion because we have the large global loop gain, and when the frequency increases, we want to get rid of the gain in the global loop to avoid having our phase shift problems. We find actually that a lot of the gain is used in this local feedback loop. So the gain of this stage, it doesn't go away as such, not until you get towards the FT of the transistors. But in the global loop we want to remove the gain, and we do that by having this local feedback which increases, the amount of feedback increases the frequency, because as the frequency goes up, C1's impedance drops. So at higher frequencies, the VA stage tends to linearize itself by virtue of having a lot of feedback around here. So it really is not to blame for very much of what's going on. Of course, as this feedback is made more local as frequency increases, there's not so much feedback to linearize this stage or this stage. And of the two of them, this is the one that has the large signals, this is the one that has the switching on and off. This one has all the nasty things. This one really isn't too bad. The signals are quite small. It's not. If you were going to make one out to be the bad guy, it would be this one. So we don't really need to discuss the distortion much more than that. If you want to know the distortion, you can do the Fourier on the time domain, or you can hook up your real amplifier to a spectrum analyzer. The key thing you need to do if you're actually going to do it in the lab is you'll put in some fundamental frequency like a kilohertz, and you will get the gain of whatever it is. It's 6 for this amplifier, which is pretty low. So you'll get 6 volts out, and you'll put that into your analyzer, and your analyzer maybe is okay with 6 volts, but the second harmonic and the third harmonic, you're hoping they're very small, maybe minus 90, minus 100 dB. Whereas 6 volts is a few dB, probably, I don't know, 10, 15 dB. So your analyzer has to be able to react appropriately to that very large change in amplitude. Of course, if your analyzer is happy with that, no problem. But a lot of the time, it will get very upset if you try and perform a sweep that has such a wide range, and you won't get very good resolution on the harmonics that you want to look at. Sort of things I'm thinking about are a regular spectrum analyzer that operates in the baseband, but there are other things you can get, like a company called Audio Precision used to make specialist distortion analysis equipment for audio. I think they still do. I've never actually used any of it. Don't know if it's any good. Standard spectrum analyzer with the correct frequency range is perfectly acceptable for this sort of thing. You don't have to you don't have to have any special fancy stuff. It's better if you can have an analog one, because the digital stuff, unless you've got some good analog circuitry to prepare the signals to go into the ADC, if you've only got a 16-bit ADC, and you'll be jolly lucky to have a 16-bit ADC on a spectrum analyzer as well, by the way, that will only give you so many dB of signal to noise ratio. And of course you're trying to measure very widely disparate size signals between your fundamental and all your distortion products. So you've got to be a bit careful. You can't just FFT your scope result and hope for the best, because the scope's probably only 12-bit ADC and they need that for the speed. So the trick is that you filter out the fundamental and you only look at the distortion products, and then you can gain up your spectrum analyzer to whatever you need to get a reasonable resolution. But anyway, we're a bit off topic now. If you want the distortion, just take the Fourier in the Spice and it'll be broadly alright. I mean, you would take it as the best possible case and know that in the real world it will probably be worse. Now we're more or less done with noise, I think. Don't want to dig too deeply. Other thing you can do with the noise is you can look at the particular quantities. So when I was doing my PhD, which was about 5 years ago, you couldn't use Spice to tell you what each individual part was. You could click the transistor and it would tell you how much that transistor caused at the output in terms of noise. But if you wanted to know if it was shot noise in the collector or shot noise in the base or flicker noise, it couldn't tell you. But I suspect, I think I saw a while ago, it will tell you the noise due to the internal resistance of the collector, the noise due, this is thermal noise due to the internal resistance of the emitter. This is the shot noise of the collector, the shot noise in the base, the flicker noise in the base, and the total. So you can go and find out which is the most important one. Funny, I thought it would be that one and it's not. So there you go. That's the collector shot noise. I guess it's probably the base shot noise then. I'll tell you what, I'll just change this one and we'll see. So that's about 3.9 nanovolts per root hertz. There we go, yeah, it's almost all base shot noise. Of course, when you couldn't do that, you had to sit down and work it all out by hand, or use Maple or MathCAD or something like that to do the maths for you. If you really wanted to hurt yourself, you could try and use MS Excel, but real scientists don't. Never mind, Bill, I'm sure you've got enough money. So that's something nice that you couldn't do that you used to be able to do. That's progress for you. Righty, let's just have a quick look at the power in the output stage, because I didn't cover that anywhere else and I probably should have. Get rid of that, put that back to 3 milli, make that a nice sine wave. Kilohertz will be fine. None of the rest of it. Run that. I'm interested in the power dissipation. So if I was to take that lot, which is the power in the output transistor, high side, and add it to this one, I'll get one waveform that gives me everything. And then if I was to take the average by pressing Control, it'll tell me the average is 7.325 watts. So about there, in other words. That seems believable. So this is with the output of a volt. Now if I was to change this slightly, maybe I could do, I don't know, I'll call it V in, and those curly braces make it a parameter, and I can set a param, step param V in list 0.1, 0.25, 0.5, 0.75, 1, 1.25, 1.5. Don't want too many, that probably is too many. And we should get... fair enough. Oh, power, P-A-R-A-M, AM. Yeah, there we go. Got to learn to spell. Very important. There we go. Or we could go a bit further. Maybe. A bit further still. Or I could reduce the supply voltages. That would give me the same, because I put them up to 20. And originally, the person emailed me asking for 15. Oop, I missed a 2 then. There we go. Now we've got this little bit here, that maroon line, it goes up, then down, then up. So this, now what's happening in terms of the voltage at the output, or the current in the output, is that we're only getting bigger and bigger currents and bigger voltages. We're still not really pushing this amplifier very hard. We could probably go a bit further still, because the gain is pretty measly. 3 6s are 18, supply rounds are 20. Better stop there. It's just clipped on the top. So let's take it, delete the last ones. We don't want to see any non-linearity. It confuses the picture. We're really into 223 territory here, but I don't think anybody will mind. So we can see we've got sine waves and they're just getting bigger. If I delete this top plot pane, you can see certainly in the highest amplitudes at output, we've got this big dip in the middle. The reason is, as this node goes up in voltage, there is less VCE across this transistor, because this resistor is getting it all as the current passes. The current flows in the resistor, jacks up the voltage on the output node, and of course that means that the supply minus that is what drops across VCE. As your VCE is dropping, even though your IC is going up, VCE is dropping proportionally more. Consequently, as you get towards the peak excursion of the current or the voltage in the load, you actually find the output, the power in the output stage, dissipated as heat, is dropping briefly. And of course the temperature doesn't change, because the thermal time constant of the parts and the heating and so forth is very large. But if I said to you, find me the worst case output stage power loss, not the power in the load, the power lost in the output stage, to give me the highest temperature that we'll ever get to, and you went for the biggest input voltage you could, thinking that that would give you the worst case, well, it doesn't, because that would give you this case. And if I just delete the step command, so that's 2.75, that one. That's an average power of 8.79. But if I went back to something where it had a more or less flat top, lower amplitude of input, I don't know, should we say 2? I can't remember, I could go and have a look. 2's pretty close. A bit less than 2. Maybe 1.8. Okay, 1.6. .7. Yeah, there we go. It's just starting to dip a little bit in the middle. Now if I took the average of this one, 9.5, which is more than 8 point something. So if I was to plot a graph of the maximum power, or the average power in the output for a given input, I'd have on this axis, let's draw a little graph, not a real graph, one of my imaginary graphs. There's my axis, and this axis is going to be Vn. Wow, that's tiny. Please don't make your graphs like this, because no one can ever read your axis labels. Please make your symbols nice and big. And on this one we'll do power loss in output stage. Now I've got to try and draw a curve. definitely feeling the limits of you'll probably get something. Oh, beautiful. Okay, not that beautiful. It was going quite well. That's supposed to be a nice curvy curve. There's a bit of a hump here, but never mind. If you went for the biggest V in, you'd end up somewhere here. But actually, if you're looking for the biggest power loss, you'll find it somewhere in the middle. Probably between about 1/3 of the maximum voltage and 2/3 of the maximum voltage. It depends to some extent how much above the maximum swing your supplies are going to be. You need lots of headroom. That will change a little bit where this graph lives on these axes. The shape won't change very much, but if you say you're going to have 50 volt supplies and you only need to have 20 volts of swing, your power loss is going to be a lot worse. Just because your VCE will never drop as much, because you're always going to have a lot of headroom, and you probably wouldn't want to do that because it makes your amplifier inefficient. So need to be a bit careful when you're doing your calculations in this regard, that you don't jump to any conclusions about what is the worst power loss, because it might not be where you think it's going to be. Power in the load, I press Alt there by the way, and I got the little thermometer. If you're running a Mac, you need your head examining obviously, but if you are running a Mac, there's lots of funny different keys and I don't know how to do it, but if you Google it you can get the little thermometer symbol to come up. Yeah, anyway. So the power in the load, control click, 6.49, power in the output stage, oh dear, press the wrong button, power in the output stage, 9.5, efficiency, less than 50%, and that's with the sine wave. So, oh dear, we can get better efficiency, slightly increase that to 2.1, so 7.5 is the biggest, wasn't it? This should improve our efficiency quite a bit. 17 watts out for about 8 watts in. So what's that? 17 upon 8. 8 upon 17, sorry. Is that right? No, hang on a minute. It's not that simple. We've got total power in the bottom and power we care about on the top. 17 over 8 plus 17, there we go. 42% efficient. God, that's pretty miserable, isn't it? Is it really that low? No, maybe it is. Sure, somebody email me and tell me that's wrong. Did I really do that right? 17 watts out divided by 8 watts lost plus 17 watts expended. Yeah, 68% efficient. That's better. Times 100 to get percent. Good. I blame the calculator for that. Certainly wasn't my fault. It transpires that you can do not a long-winded proof, but a bit of a proof. In fact, I think I set it in one of the 225 tutorial sheets about this output stage. The maximum efficiency you can ever hope to achieve, and it's about 70 point something percent. The thing is, of course, that this is with a sine wave, and if you're trying to drive an electrical machine or something on a variable speed drive, you might want sine waves, and you might want to have maximum amplitude all the time, and the only thing you change is the frequency, perhaps. And that's quite common if you want to drive an induction machine or a synchronous AC machine of some kind. If you want to play music, you certainly don't want to listen to sine waves, because it's jolly boring. And also, at this sort of volume, it'll be pretty loud. So you want to play music, and music has an unbelievably high peak to average ratio, which is to say the peaks, like the bass drum kick or whatever, are extremely transient and they have a high value, but a lot of the time the actual power that you have in the room is probably less than a watt. Even in a big venue, I shouldn't think the average power is more than about 5 to 10 watts, even though they'll have thousands of watts of amplifier sat about. Got to remember, of course, that loudspeakers are unbelievably inefficient. Be lucky if you get a couple of percent efficiency from a loudspeaker. but human ears are unbelievably sensitive and easily damaged. You must look after them. Wear earplugs, that sort of thing, if you go to gigs. Even if everybody thinks you're an idiot. So, a little bit about the output stage. I think I've probably covered enough. No doubt there's much that hasn't been said, but we did a bit about the design of the current sources, the overall feedback, we dealt with the mirror. We never actually just ran this in open loop to get how it takes the difference, which you could do if you wanted to. Easiest thing to do would be build yourself with just a regular current source, as in something like that, to replace all this lot, and a couple of resistors down here in the beginning, a couple of voltage sources, and you plot a map, which is one line that does that, usually has another line that does that. You'll be able to get Spice to plot it. If you go on the Yahoo group for it, there'll be some sort of explanations. The Yahoo group's very good, full of clever people who've been using this for a long time. Something else we didn't deal with is the input impedance and the output impedance. Maybe we ought to do that. Might be a good idea, actually. Let's have a quick go at that. So if I wanted the input impedance, I'd measure the current flows into R99 and have the voltage on this node, divide one by the other, it should give me the value. So I'll run an AC simulation, because we are doing this in small signals, and small signals we're calling AC. So I can get rid of that, don't need that anymore, don't need that anymore. There's one, there's the other. So R is V upon I V3, done. Get rid of that one, don't care about that anymore. And let's try and put it in log, shall we? So we've got 10 megaohms small signal input impedance. Don't forget, we're still going to have the DC current flowing out of here. But as far as the small signal is concerned, enormous input resistance. Reasons for that? Well, the way the feedback, global feedback, is derived and applied is derived in parallel with the output, because effectively this voltage is with respect to ground and the output is across here to ground. So this feedback pathway and this resistor in parallel with each other, so it's parallel derived, or shunt derived if you prefer. Series applied because the input coming in here makes a current in the emitter in this node, and this current is a part of this current because this is the current that's shared out between these two transistors. So the input comes in and we get a current in this side, and the feedback comes in and we get a current in this side, and these two currents must sum up to this current source value. So the subtraction of the input signal and the feedback signal is done as a subtraction of currents effectively on this emitter node, in this emitter branch, and the result of that is the currents that flow in the collector. So the feedback application is in series with the input, in as much as they're not in parallel with each other as this one here and this one here is. They actually come together on a node, and that's usually called series. It's not easy to see. Have a look in grey at the feedback chapter if you want. I still don't pretend that it's easy. This feedback is a funny old thing. It behaves in ways people often don't expect. Anyway, that's my interpretation of it. So the feedback acts to increase the input resistance, and the degeneration of these two, this differential pair with R1 and R2 acts to increase the input impedance, and the fact that we've got current source here instead of just a resistor acts to increase the input impedance as well, and we get very, very high. 10 megaohms is very nice. And by the time you get to 20 kilohertz, which is the highest frequency we really care about, we're down to probably 200 kiloohms, I should say. 420 kiloohms, alright, looking a bit low down. So half a meg, that's perfectly acceptable. Very good. If I wanted the output resistance, usual method, delete the load, get a current. You can use a voltage as well if you prefer, but I will drive in a current. Maybe an amp, doesn't really matter because it's a small signal. When I say it's a small signal, what I mean is Spice is taking all the Ebers Moll or Gummel Poon models of each transistor and calculating the operating point for us, working out the GM and the RBE and the RCE and the CCB and the CBE and all the other little things that go into the full model. And it's making a really big matrix containing all the nodes and branches and all the passive components as well, and then it's running that small signal simulation just the same as if we sat there with a pad and a pen and did all those calculations ourselves. That's all it's doing. The only reason we use a computer to do it is because it would be unbelievably tedious and difficult for us to write out such big sets of equations and then to solve them. Spice can do it easily because it does it all with numbers. And of course you've got plenty of memory and it solves things as a computer solves them rather than as people do it. So it doesn't matter that I think an amp is a small signal, because once this circuit has been converted to a small signal model, you can put a mega amp in if you want, and the simulator will think that that's a small signal. And the reason it thinks that is because it treats everything as a small signal once it's made that jump into the small signal analysis. It's up to you to make sure that an amp really is a small signal, and if it's not, more fool you for putting it in. Since I just want a resistance, and I want to do R is V upon I don't want to have to divide through by 10 milliamps or something. If I just put an amp in and remember that I can't really put an amp in, it'll be okay, because all I want is the answer from the calculation, effectively. So, did I run it? I didn't run it. Oh, I've got to switch this off. Got to switch off your input. Got to ground the input for this bit because we're driving the output. All other things are a superposition. This is not a DC source, so we'll switch it off. Got to have the DC because it sets up the DC conditions. So V out upon I1, if you like, but I1 is an amp, so I don't need to divide through. Our output resistance never gets above 1.42 milliohms. That's a little m for milli. That's very low. Excellent, in fact, because we want to drive this 8 ohm load or 4 ohm load, or if you want to do a subwoofer in a car, 1 ohm load possibly. You don't want to have a lot of power lost in the insides of your amplifier, because that won't end up coming out as noise in your speaker. You wouldn't want to have a potential divider of this lot and your load. Effectively what we're saying is, my whole amplifier is a voltage source, and I've got a resistance in series, so a Thevenin source, and this is my output, and my output will go to some load that I may or may not choose to plug in, and this resistor here at 20 kilohertz is 1.42157 blah 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 ohms, milliohms, oh dear. 0.00. Yeah, that's it. Very small. Of course, as frequency goes down, the internal resistance actually drops very, very low indeed. We're down way below the resistance of the wires that we're using even to plug the speaker in now. The reason it's so low is because the parallel derived series applied feedback acts to increase the input impedance, which is why the input impedance is much, much bigger than just the RBE of this transistor, and decrease output resistance, which is why the output resistance is much lower than the 0.22 plus the resistance we see looking up here, all in parallel with this 0.22 plus the resistance we see looking in there. Now, if you've been in the amplifier lab, you'll know that we did an experiment quite like this in the last part of day 3, if you made it that far, where we changed the resistance of the load and attempted to see what the voltage drop was due to the internal resistance. We didn't drive a current in. It's not so easy to do that sort of thing in the laboratory. In the laboratory we use the differently sized resistors to see the effect. But we are really measuring the same property, just in a different way. So, input impedance is high, output impedance is very low. Distortion is low, noise pretty low, gain good enough, bandwidth good enough. We're all pretty happy really. It's pretty good. Put my 8 ohms back. We've worked out the power dissipation. We can probably work out the heatsink we need. If you've not done that, the usual method is to draw a little circuit. We can try and make a little circuit like this. You don't have to do it on the same diagram as the rest of your model, but you can if you want to. What we usually do is we make a little sleight of hand. I will call this voltage on this branch, or on this node, sorry, I will call it the temperature of the junction, and I will make some other circuitry as well. All the voltages will be temperatures, all the currents will be powers, and all the resistances will be thermal resistances in degrees C per watt. So degrees C temperature rise per watt of power dissipated. If you did it in a different diagram, you wouldn't have to keep zooming in. So this will be the power dissipated in the output stage, and I think the maximum value I came up with was about 9 watts. Let's call it 10 just to be on the safe side. That's 10 watts, even though it's amps, it's watts. Then we've got the transistor. This is the junction, so I could call it maybe TJ. This will be the case of the transistor, so I'll call it T case. This will be the temperature of the heatsink, so I'll call it TS. And this one will be the temperature of the air in the room, so I'll call it TA. This is the thermal resistance of the junction to case. This is the thermal resistance of the case through the pad. This is the thermal resistance of the heatsink. The thing is, when you've got multiple transistors connected to a single heatsink, as I do here, this is one transistor, Q12, this is one transistor, Q13, you have to have a little pad. And the pad has to conduct the thermal energy, the heat, but it mustn't conduct the electrical energy, the current. Reason is, when you buy the transistor, usually the bit of the semiconductor which dissipates the most power is the collector to base junction. That's because the biggest voltage usually falls there. So to get the heat out effectively, the transistor packaging people will put the collector against the metal part of the package. And that means the metal part of the package is at the collector voltage, which in this case is 20 volts, and in this case is minus 20 volts. And then what we're going to do is we're going to put a metal screw through the hole in the package and screw into a metal heatsink, one heatsink. So the two screws will be screwed into the heatsink, and the two metal packages, or the metal parts of the package, will be touching the screws. So there will be a short circuit effectively from there down to there. And of course your amplifier won't work properly. If you're very lucky, your power supply will just current limit. If you're very unlucky and you haven't got a current limited power supply, fuse will go, and if you've no fuse there'll be a bang. So we must be careful to put in a little silicon pad or a mica pad which prevents the conduction through the case of the transistor. You also have to have a little plastic flange which stops the screw from touching the metal case of the transistor as the screw passes through the case. But well, you can Google for that sort of thing and find it quite easily. So we need some representative values. Firstly, the temperature in the room. Shall we say 25 degrees Celsius? I don't know about the size of this yet, but we'll work it out. Junction to case, you get from the data sheet of the transistor that you buy. I don't remember for this one, but I think it's about 0.63 degrees C per watt. So that's 0.63 degrees C per watt, and that's the thermal resistance. And you can go and look up the TIP 3055 and you'll get the number. You're looking for junction to case there. Case to sink, that's the pad thermal resistance. When you buy the pad, you'll get the data sheet for the pad, because you look at it on Farnell before you actually buy it, or RS, or one call, or DigiKey on Mouser, or Arrow, or Anglia, or Maplin, God help you. And it's usually about 0.45 degrees C per watt. Now you might say, well, what about this one and this one? Yep, if you want to be really solid and do everything, that one, and that one should all have their own little pathway in this diagram. And if you've got a power supply that you've built for your amplifier, and you've got a linear regulator maybe, or you've got a bridge rectifier that needs heatsink, and you put that on the heatsink as well, which you could if you wanted to save money and not have more than one heatsink, you'd have to put that on too, because all the thermal loads have to be accounted for. So, last question is, what should we make it? Don't want to make this one too small a value, because you have to pay more money and it's physically larger and heavier. But you don't want to make it too big, otherwise your junction temperature will be really high. So we'll start off with our opening bid of 0.25 degrees C per watt and see how we get on. I will also put some data labels down which will tell us the temperatures. It will say volts, but they are, in our mind, temperatures. So temperature on the junction, temperature on the case, temperature on the heatsink, temperature of the air. But the temperature of the air we know is 25 degrees. That's 0. Just check I've not made any mistakes here, because those numbers seem jolly low. Simulation running. Oh, fair enough. That explains that. Have another go. It really is about 5 watts per transistor. If I went to the... Yeah, 5 watts per transistor. So about 10 watts in total. Oh well. I've grossly overestimated the size of heatsink that we would need. 25 degrees C just here. The heatsink will only be at 27 degrees, so I can make this a lot smaller. The junctions will be at 32. You can't run your junction more than 125 degrees C. And when you do run it that hot, it won't be able to do any work, because that will make it hotter, and that will lead to effectively the transistor not working properly. And the reason for that is dopants, or not dopants, sorry, the electrons that are bound to silicon atoms will start to be freed thermally, and they will end up in conduction. And the effect of that is your doping becomes less effective, because it's not just the dopants, the donors and the acceptors, which are now giving up free carriers for transport. The silicon is actually giving up free carriers as well, and it tends to compensate the semiconductor. You end up with a semiconductor that appears more intrinsic, so your P looks more intrinsic and your N looks more intrinsic, and your junctions aren't as neatly defined as they were, and it upsets your electric field profiles, and transistor doesn't work very well. So you don't want to let it get too hot, but 30 degrees is bugger all. So we can have a smaller heatsink that costs less, takes up less volume, weighs less, and not worry too much about our temperatures going up a bit. Maybe we could even go for 2 degrees C per watt. Get rid of that, don't need that. 50 to 45 degrees, you could do better still, maybe 4.5 degrees C per watt. The bigger this number gets, the radically smaller the heatsink becomes. In 0.1 degrees C is about half, in all physical dimensions, the size of 0.2 degrees C per watt. And of course half in all physical dimensions means an eighth of the volume. So and that means considerably less weight as well, because weight goes with the volume. So this is probably about where we'd like to sit. This is not 125, which is a good thing, but it probably could go higher. We wouldn't really want it to go higher though, because at 70 degrees C, this is the bit of the heatsink that you can touch easily with your hand. If you run this above 70, when you touch the heatsink, preferably with the back of your hand, not the front of your hand, don't use the pad of your finger, because if it blisters there, it will annoy you every time you touch something until it heals. Because if you use the back of your hand or the knuckle, firstly there's not many receptors there, so it doesn't hurt as much. And secondly, if it blisters there, yeah, it's frustrating, but at least every time you open a door or push a button, you don't think, ow, it hurts. So use the back of your hand, not the pad. When you get to 70 degrees C, this is about the temperature at which your reaction time is about the same time as you need to get enough energy into your skin to blister it. If you go more than this temperature, you will not be able to remove your hand quickly enough to prevent you getting burnt and a blister forming. So you don't really want the heatsink to get above this temperature. Now if you're running in some application where the user is never going to touch this part because it's somehow mechanically shielded from the user and they can't get their fingers in, even a small child cannot get their fingers through the tiny gaps. There will be gaps because there has to be airflow. But make sure no one can touch it. You can run as high as you like, up to a junction temperature of about 125, if you're not going to do any work at that temperature. And obviously if you want to go higher than that for some reason, you can try using a different semiconductor. Maybe a gallium nitride or silicon carbide transistors can run 200-300 degrees C. Probably not much problem. If you run very hot though, you will find that things start to burn off. So if the heatsink, when it was made, had a residual film of oil on it and you run it very hot, you'll get a smell from the oil that's burning off. And if it gets dusty, it's like turning on a heater after the summer when the winter comes. It stinks of the smell of burning dust for a few minutes before it all burns away. So there are other reasons you don't want to go mad with the temperature. Also, the harder you run them and the higher the temperature you run them at, the shorter their life will probably be. So you don't want to exercise them unnecessarily. But 4.5 degrees C for watt's pretty small. You could probably fit 5 transistors on it, no problem. These 4 plus the one that's off the edge of the screen, which does our thermal compensation. And that would be the mechanism of design. You can do this on a bit of paper. You don't have to have a SPICE circuit to do 4 resistors and 2 sources. But if you wanted to do it in SPICE and just tweak this to the numbers you like the look of, having just got the power right then, you could do it. I bet you, if you wanted to, you could even make this a behavioural source, which used the power taken directly from this simulation, but there really is no need. We can tell it's about 10. That's good enough. Righty. I don't think there's much else to say now, although I have said that several times before and I always find something else to talk about. I think we're more or less done. Righty, bit of luck. This has been helpful if you're taking 225. If you want to get into some analog design, if you're doing the amplifier design project in the 2nd year, if you're doing your thesis in your 3rd and 4th year and you have to do some analog work, or MS, or if you're just interested in amplifiers or analog design, that sort of thing. It's not all amplifiers, of course. There's timer chips and voltage references and ADCs and switch capacitor circuits and charge pumps and current mode systems. We haven't talked about translinear circuits, mixers, all kinds interesting things live out there, waiting, oscillators waiting to be discovered. Anyway, I think that's probably enough from me.